I would like to welcome everybody and thank you for joining us for today's webinar, which is the latest in a series funded as part of the FDA project, a targeted learning framework for causal effect estimation using real-world data. Each webinar is recorded and posted on the internal FDA intranet and also on YouTube for public viewing at any time. And slides can be downloaded from the Putnam Data Sciences website at putnamds.com. Today's talk is on practical considerations for specifying a superlearner. It's presented by Rachael Phillips, a PhD student in biostatistics at UC Berkeley, who's advised by Dr. Mark Bantuan. She has a master's degree in biostatistics and bachelor's degrees in both biology and mathematics. As a student of targeted learning and causal inference, Rachael's research involves semi-parametric statistical estimation and inference. She's currently working with Dr. Romain Paracchio on a personalized online superlearner for intensive care units, and is also a key contributor to this FDA-funded targeted learning project. So Rachael, thank you for joining us today, and I would like to turn everything over to you for your talk. Thank you very much for being here.
Thanks for the intro, Susan, and thank you everyone for attending this talk. Okay, so today we're going to talk about practical considerations for specifying a superlearner. Superlearner is a machine learning algorithm that uses cross-validation and a loss function to optimally combine the diversity of candidate algorithms into a superlearner ensemble. The superlearner is extremely flexible and entirely pre-specified. But how should it be constructed? The superlearner is proven to be asymptotically as good as the best candidate algorithm in the library. So how can one ensure that the candidates are performing as well as possible? In this talk, we provide a flowchart for constructing a superlearner in practice, discussing relevant arguments, and recommending specific inputs. The machine learning algorithms are going to learn associations in the data between the covariates and the dependent variable or responsive interest. How much you can learn to do depends on the complexity of the prediction problem and on the amount of information in the data. So when you have more observations, you're able to learn more than when you have fewer observations. It's not just the number of observations you have to take into account when thinking about the information in the data. It's more generally the sparsity. The sparsity encompasses the number of observations, of course, but also the prevalence. So if you have a rare binary outcome with 1 million observations, but the majority of them are only ones, and only a small fraction are zeros, then you still have limited information despite this large sample size. This brings us to the idea of an effective sample size, which we will use to serve as a proxy for the amount of information in the data. And it's going to impact the number of cross-validation folds, and it's also going to impact the choice of algorithms that we choose to put in our superlearning library. Algorithms with more structure, like parametric models, use modeling assumptions to smooth over areas of low support in the data. And so if we have a small effective sample size, we don't have to restrict ourselves to these parametric models, but to more structured machine learning algorithms like Lasso that do covariate selection, or some of the tree-based algorithms. But some of the algorithms that require more data, like neural nets that typically have so many weights, they need lots and lots of data in order to fit all of these parameters, maybe are less appropriate with a small sample size. So ineffective in this idea of effective sample size, and more generally, the amount of information in the data drives almost everything about superlearning, except perhaps the choice of the loss function. But even then, it might make us choose to do discrete over ensemble superlearner. And so first, we'll talk about what I mean with effective sample size, and then how does this affect the choice of cross-validation folds, the choice of algorithms in the library, also what loss function do we use, and how do we combine the algorithms. So here's the outline. First, we'll go over a step-by-step specification of the superlearner, going through the flowchart. This involves determining the sample size itself and then calculating the effective sample size from it, specifying the number of v-folds for the v-fold cross-validation scheme, defining a library of candidate algorithms to be used in the superlearner, choosing a loss function and then a method for weighting these candidate algorithms. And then after this, we'll go over a few examples using superlearner in the context of causal effect estimation. Okay, first step is to calculate the effective sample size. The first step in deriving the sample size is to the effective sample size is to quantify the sample size itself, N. We'll define the sample size N as the number of independent and identically distributed observed units, which may or may not be equal to the total number of observations. Okay, moving on. Is the dependent variable binary or continuous? We're focusing on either binary or continuous dependent variables in this talk since they are most common. Of course, you can have a multivariate dependent variable, you can have categorical dependent variables, but they're not as common. If the dependent variable is continuous, we're going to say that the effective sample size is N, the sample size itself. Now, for binary dependent variables, first we want to identify the number of observations that correspond to the dependent variable with the lowest rate of occurrence. Here's an example where N is very large, but one of the levels of the dependent variable, y equals 1, when the event occurs, happens far less often than the other level, y equals 0. Here, 60 is N rare, the level of the dependent variable with the lowest rate of occurrence. And now that we have N rare, we can calculate the effective sample size as the minimum between N and 5 times N rare. So in this case, we would say that the effective sample size is 300. It's important to keep N rare in mind when we specify the superlearner, not just the effective sample size. And we'll see this shortly, as well as in the example. The reason we chose 5 here is based on the same logic from case control studies with a limited number of cases. Specifically, that the statistical power of the study can be increased by having more controls than cases, but ratios greater than 4 controls to 1 case have little impact on power, and thus little impact on the amount of information. Again, this is just a simple rule of thumb to ballpark the information that's available in the data, and we'll use this effective sample size in the next step. Okay, step 2. Define the v-fold cross-validation scheme. We focus on v-fold cross-validation since that's most commonly what we'll be dealing with. As a brief refresher, we include an example with 5-fold cross-validation, and we'll also have a mini review of the superlearner ensemble itself. Say this green box is our data, and we want to use 5-fold cross-validation. First, we split the data into fifths, and across the 5 folds, we alternate which fifth is used for testing and which 4/5 are used for training. In the end, we see that we have 5 iterations of the data set, and we end up testing on all of the observations in the data. Also, testing means that we give a trained algorithm new covariate data, and it returns predicted outcomes. We can then use those predicted outcomes to evaluate the algorithm's performance relative to the observed outcomes in the test data. And these observed outcomes in the test data weren't used for training, so this is a fair evaluation. In order to do a good job predicting the outcomes from the test data covariates, we need an algorithm that's been trained on data which is representative of the entire sample. And this might mean we need to add more folds so our training data is larger. If we had 10-fold cross-validation, 9/10 of the data would be used for training. So increasing the folds increases the training data. All right, let's focus on the predicted outcomes across all of the test data in all the folds. We note here that there are all of the observations contained in these predictions from the test data. And these predictions are often referred to as cross-validated predictions. We can compare these predictions to the outcomes that were observed by calculating the loss between the observed and predicted values. One example would be the squared error loss. We can then take the mean of all of these losses to summarize them and obtain the mean squared error. We refer to this summary measure as the cross-validated risk. To put things in perspective, I note that this is just a set of predictions from one algorithm. In practice, however, we have the cross-validated predictions from a library of candidate algorithms. We refer to this matrix of cross-validated predictions as the meta-level data, this purple matrix here, and here are our outcomes. We subsequently used the meta learner on this meta level data to assign weights to the candidates and establish the super learner. We have two classes of meta learners. First, the discrete super learner selects the algorithm with the lowest cross-validated risk, giving it a weight of 1 and all of the other algorithms a weight of 0. So here, candidate 7 would have the lowest cross-validated risk, and the discrete superlearner would give it a weight of 1. The ensemble superlearner, on the other hand, can assign positive weight to multiple algorithms in such a way that the cross-validated risk for this weighted combination is minimized. Ensemble superlearners can be as simple as fitting a linear model, regressing the observed outcome on the cross-validated predictions, and using the returned coefficients as the weights. All right, now that we're caught up with that refresher on V-fold cross-validation and superlearner, let's move to the next step of the flowchart. We'll use the effective sample size to decide on the number of folds for V-fold cross-validation. Remember that we want our training data to do a good job, so we need it to be representative of the sample. We can see that as the effective sample size is increasing, we decrease the number of recommended folds. When the effective sample size is less than 30, we recommend leave one out cross-validation. When it's less than 500, at least 20 folds. Less than 5,000, at least 10 folds. Less than 10,000, at least 5 folds. And greater than 10,000, at least 3. These decisions were made so that we would have training data that's representative, so the number of folds can be smaller when we have a much larger sample size. Okay. There are a few other decisions that we can make with the cross-validation procedure when we have more than one observations in the validation data. Firstly, are the units IID? And if they're not, we need to specify a clustered cross-validation procedure according to a cluster identification variable. Clustered cross-validation forces observations in the same cluster to be in the same validation fold. This ensures that the training and validation samples are independent. An example when we would need this is when we have repeated measures data and the same subject is represented several times in the data. Clustered cross-validation will ensure that the same subject is never split across training and validation data for the same fold. Stratified cross-validation. This is what we would recommend when the dependent variable is binary. Stratified cross-validation stratifies the data splits by the binary dependent variable, attempting to maintain the same ratio in training and validation sample data. So if we have an event that occurs 10% of the time, we would try to maintain that 10% occurrence in the training and validation samples for each fold. Okay, now let's look at how we can specify the library of machine learning algorithms to be used as candidates for the superlearner. First, we want to keep in mind that we should consider a variety of different algorithms, and we can also consider the same algorithm tuned with different plausible settings. And this is to estimate the prediction function for the dependent variable. The library should be able to adapt to a diversity of true functional forms. So it's not enough to include 3 parametric models or 3 of the same type of learning algorithm in the library. It needs to contain a diversity of different algorithms so that it can adapt to potential true functional forms, which we don't know, but we are trying to learn. Also, the library should be justified, and it can be justified in terms of the prediction problem itself, the statistical model, the effective sample size, and the number of rare outcomes if the dependent variable is binary. Also, we should take the number of covariates into account if we have a high dimensional sample space, for example, a high dimensional covariate space. Okay, let's get to the recommendation. Everything that follows will be part of the recommendation. And I'll use this glow to highlight where we are. So consider parametric and penalized regressions such as lasso, splines, and stepwise regressions. Tree-based methods, generalized additive models support vector machines, neural networks, each with tuning parameter variability. Just as a reminder of what I mentioned in the beginning, when the effective sample size is quite small and we have low information, we need to be a little bit more careful with the algorithms, including ones with more structure that can smooth over areas of low support in the data. If we have some continuous covariates, we should keep in mind that we can include algorithms that don't enforce linear or monotonic relationships between variables. Some of these we included above, but we just list them again here. Regression splines support vector machines and trees. Even if we don't have continuous covariates, we still end up at the same spot in this flowchart. Is the number of covariates greater than the effective sample size divided by 10? This is just a rule of thumb to try to figure out if we have a high dimensional covariate space. If we do, then we recommend pre-screening. So this would be coupling each algorithm that doesn't perform internal covariate selection, with at least one pre-screening algorithm, in addition to a version that retains all covariates. Pre-screening will reduce the covariates that are supplied to another algorithm, sort of like a pipeline where we can reduce the set of covariates and then only give those covariates to the algorithm, such as GLM. And we can use lasso pre-screening to select the covariates that have a non-zero coefficient in a lasso regression and only pass those covariates to the GLM. Also, any algorithm can be coupled with pre-screening algorithms and included as additional candidates in the libraries. So we can include a GLM with pre-screening and without, or a tree with and without pre-screening. Also, there are some innocuous types of pre-screening that we can incorporate by removing highly correlated covariates, getting rid of sparse binary covariates. The pre-screening will reduce the computational time And so it can be really useful in some settings depending on how high dimensional the data is. Okay, finally, including as many algorithms as possible is recommended, with the effective sample size divided by 5 as an upper limit for the discrete superlearner, and the effective sample size divided by 25 as an upper limit for an ensemble superlearner, taking into account the computational time and the resources that are available. We have a higher upper limit for the discrete superlearner because it is less prone to overfitting than the ensemble superlearner. And the ensemble superlearner will create this weighted combination, so it adds to the diversity of the algorithm. Okay. Next, choose a loss function and the method for weighting the candidate algorithms in the library. First, we want to select a valid loss function that identifies the desired measure of performance. A valid loss function is one which is bounded and its expectation is minimized by the prediction function under the true data generating distribution. Here's an example. When estimating a conditional probability distribution for a binary dependent variable, the negative log likelihood loss, squared error loss, and AUC loss are all valid loss functions. If our desired measure of performance is to perform classification, then maybe the AUC loss would be more appropriate. If, however, we're estimating a propensity score, then the log likelihood loss or squared error loss would be better than the AUC loss. So we can choose the loss based on what our aim is with the prediction. After selecting a loss function, we want to choose a meta-learner that we can use to assign weights to the candidate algorithms. The meta-learner is just the method for doing this. We spoke about this earlier. The cross-validated selector or discrete superlearner assigns a weight of 1 to the algorithm with the lowest cross-validated risk and a weight of 0 to all other learners. The ensemble superlearner is a meta-learner that assigns weights to algorithms such that the cross-validated risk across all of the weights is minimized. Multiple algorithms can have non-zero weights here, and restricting the space of possible weights to be a convex combination enforces the same bounds on the predictions. We note that the weights are subsequently applied to candidate algorithms that have been trained on all of the data, so full fit predictions, in order to obtain the superlearner predictions. And we recommend discrete superlearner, where we select the best candidate algorithm from the base learning library. Also ensemble superlearner with a convex combination of the weights such that they are non-negative and sum to 1. Also, you can use an external round of cross-validation to select among ensemble superlearner candidates and individual candidate algorithms fairly. You can also use the external round of cross-validation to examine the performance of an ensemble superlearner on unseen data. Okay, specifying superlearner examples. These are all in the context of causal effect estimation. And here's a fictitious example based on this acupuncture for chronic headache in primary care randomized control trial. So here's our clinical question of interest. How does headache medication impact headache severity? And we want to answer this question with respect to adults who have chronic headache. Our treatment is to randomize 3 months of medication taken as needed or usual care. Later, at 4 months, we'll measure the headache score. The intercurrent events here are loss to follow-up, which we'll refer to as delta, and delta equals 1 if the outcome is observed, delta equals 0 if the subject is lost to follow-up. And treatment noncompliance, but that's not really relevant here since we say take the medication as needed. There is no protocol for taking the treatment. Our summary measure is the additive effect of this medication on the headache score at 4 months under no loss to follow-up. So just noting that the causal estimand reflects the clinical question of interest as well as the relevant intercurrent event. Here's our causal estimand with the counterfactual setting no loss to follow-up, delta equals 1, and then comparing the outcomes under receiving the treatment versus receiving the control. Here's our statistical estimand, which is defined with respect to the observed data. These two quantities are equal to each other when causal identifiability assumptions are met. We're not going to go into that here, but we do estimate psi observed, the statistical estimand from the observed data, and we'll use TMLE with superlearner to estimate it. We'll use superlearner specifically to estimate these components: the propensity score, the missingness mechanism, and the conditional mean outcome. Okay, our observed data. We sampled 401 subjects, and at baseline, we collected some covariate information and then also randomized them to treatment. Here's some of the covariate information and then randomizing them to the medication A. Later, at the end of study, we lost 50 patients, so 50 didn't show up to the last appointment. And we observed their headache score when they showed up. Otherwise, we don't observe it. And that's why we have this delta Y together here, because technically the subjects do have a headache score at month 4. We just don't observe it. Okay, let's get into the different specifications for the superlearner for each of these components. We'll go through listing the dependent variable, covariates, effective sample size, cross-validation scheme, library, and then we'll justify the superlearner library, and then the loss and meta-learner. Okay, propensity score. For the effective sample size, it's the sample size itself because that's smaller than 5 times the number of people that were randomized. For the cross-validation scheme, since our effective sample size is less than 500, we recommend V equals 20, and we have a binary dependent variable, so stratified cross-validation. The superlearner library is pretty simple here, and we note that there might be chance imbalances in the treatment randomization, so we want to adjust for those by estimating the propensity score. We want to include any potential confounders, so we consider a few different parametric regressions to model the propensity score, some perhaps with more or less confounders than others. We want to take full advantage of the treatment being randomized, which means we want to ensure that the root and consistency of the propensity score estimator is preserved. In order to do this, we use a discrete superlearner to select one parametric model from a set. This way, we end up with one parametric regression model that's fit on all of the data. We just use superlearner to decide exactly which one. Okay, moving on to the missingness mechanism, predicting the conditional probability distribution that the outcome is observed given the treatment and covariates. Here, the effective sample size is 250 because we lost 50 subjects, and that was our in rare. And again, v equals 20 was stratified cross-validation. We're going to use generalized linear models with and without lasso pre-screening, generalized additive models, regularized elastic net, GLMs, and discrete Bayesian additive regression trees, BART. Here, loss to follow-up is somewhat rare. It only occurs 12% of the time, and our N rare is only 50. And the library is slightly ambitious. So we use the discrete superlearner, and we couple with pre-screeners to establish candidates that are less prone to overfitting. For the loss function, we use the negative log likelihood and a discrete superlearner. Okay. For the conditional mean outcome, our effective sample size is 351, since that's the number of samples that we observed. We use v equals 20, and the similar algorithms that we specified for the missingness mechanism, except we also included random forest and XGBoost, or just a boosted trees implementation. This library can adapt to a diversity of true functional forms in a robust way, and the effective sample size is reasonable here. The dependent variable is continuous, so we can safely add more complex algorithms that learn complicated but potentially relevant interactions. We use the squared error loss, which is valid for estimating a conditional mean, and then an ensemble superlearner with a convex combination of the weights. Okay, we fit a superlearner to estimate this conditional mean outcome for the observed individuals. And then we use the superlearner R package with the CV superlearner function so that we could examine the performance of the superlearner on unseen data. Here we can see the performance. It's ranked from top to lowest. So the superlearner does indeed have the best performance. And this is a fair metric since we are testing the superlearner's performance on unseen data. And then we can see the other algorithms and how they were ranked. So this is how the output would look. And this underscore, this underscore with all means that we used all covariates when fitting this generalized additive model. And this is an elastic net regression with alpha of 0. It's a ridge regression. And then something like this, screen.glmnet, this would be where we fit a lasso model and see which covariates have a non-zero coefficient, and then we only give those covariates to the generalized additive model. So it's interesting to see that the screen with the generalized additive model and without screening, they both did quite well. Here's our lasso with all of the covariates included. And we also used Bayes' generalized linear model, an elastic net regression, generalized linear model. This would be a discrete superlearner that for each inner cross-validation fold is selecting the best learner. And then we have a few of the same learners with the lasso screening, a discrete Bayesian additive regression tree, multivariate adaptive regression splines, random forest, and then another multivariate adaptive regression splines with all covariates, and a boosted tree implementation, XGBoost. Here we can look at the weight that was assigned to each of the learners by this convex combination superlearner. And we have the mean weight because for each outer cross-validation fold where we're examining the performance of the superlearner, we get a new fit. So we can just take the average of the weights across all of those 20 fits. We see that this generalized additive model was selected a lot, and it received a max weight of 0.55. And also the lasso was often selected, as well as a random forest. And I didn't include the learners that were given a weight of 0. So this beige GLM did receive a weight at some point, just its mean was 0. Okay, so here are some helpful references for learning more. We have the Superlearner 2007 paper, Superlearner and Prediction, an Applied Superlearner paper for predicting mortality in the ICU. And then also here are some software tutorials for Superlearner R packages. I actually use this guide to Superlearner to obtain the table that's right here. So the function to do that is there. And then also I wrote a super machine learning tutorial with another Superlearner implementation, SL3. Here is the R code for specifying that Superlearner with the CV Superlearner. Sometimes I needed to define a special learner that wasn't available. It's very easy to do. You can see it just took one line. And then all I did was specify the candidates, set the seed, and cross-validated the superlearner fit using non-negative least squares as the meta learner, and it's normalized, so all the weights sum to 1. Also, this is how I generated the plot and that table. Okay. Thank you very much. I see I ended a little bit early, so that's nice.
So thank you, Rachel, for going over all of that. I know that when people start to use super learning, you sort of have to take a deep breath and say, how do you even begin? So I would like to invite the attendees, if you would like to ask any questions. This is the first time we're using Zoom for this webinar series. So down at the bottom of your screen, there's in the bottom panel, there's something that says Q&A. So if you want to ask any questions, I believe you just click on Q&A and a window will pop up and you can type your question there. And then when it shows up, Rachel, I'll read it out to you and you could respond. And in the meantime, while we're waiting to see if participants have any questions, I would like to ask you.
There is a question I see in the chat as well.
Oh, that's okay. That's good. Okay, then let's go to that one first then. I actually don't see it. Could you read the question?
It says, how are continuous covariates typically handled in these methods, e.g. lasso in pre-screening? So it just depends on the algorithm that you're, like the candidate algorithms that you're using. Do you have anything more to add, Mark or Susan?
The question is continuous covariates?
Yeah, how are continuous covariates typically handled?
Are they, I mean, I don't think there's anything special, right, about continuous covariates. So they're handled naturally by any algorithm. I mean, it's different. Yeah. So, and there's no reason to discretize continuous covariates. I mean, you can, but it's really no reason. I think it's generally more a loss of information. But on the other hand, if your algorithm is not very aggressive in trying to learn the functional form of your continuous covariate, then it might be useful to discretize and create a bunch of indicators for the different levels, and then add them all as main terms, for example, in a GLM net, in a lasso, so that you are still, in a flexible way, fit the true function. So anyway, yeah, so these are choices.
And this is Susan. I guess I would add a little onto that. This goes back to what candidates are you going to include in your library. If you have a continuous covariate and all you have are main terms, logistic regression, or even lasso models, then you're imposing a monotonicity assumption that may not be warranted. And so, as Mark said, if you discretize and put in those individual ones, you start to relax that. But of course, a tree-based method, presented with a continuous covariate, will just choose cut points and make splits, and there's no monotonicity assumption in there. Also, a tree-based method is going to be immune to, or it'll be invariant to transforms of the continuous covariate that preserve the monotone transforms of the covariate that preserve the ordering. And so, if for example, if like the appropriate relationship is on linear on the log scale, you'd have to actually put that into a main terms model, whereas the tree would just discover it. So for superlearner itself, it doesn't care if the covariates are continuous or not. But from the analyst perspective, choosing what algorithms you include in the library will help you more flexibly exploit the information in the continuous covariate.
Yeah, and also, as we saw in the example Rachel showed, it's not necessarily true that these algorithms which are more adaptive, that they will do better, right? This is all very much a function of the complexity of the true problem and so on. And that's what you also saw in the example, that actually in the end, it was the random forest and the XGBoost which were doing the worst relative to simple lasso type algorithms. So these things can all happen. And that's, again, shows it's important to think about general adaptive non-parametric type algorithms, but at the same time, you cannot bet on them because it all depends on the problem, what's going to work better. And so you want this whole range from parametric to semi-parametric to eventually highly flexible. And one of the algorithms to keep in mind, certainly in the future, is the highly adaptive lasso, which is also very non-parametric, but also has a whole range of fits by specifying the L1 norm. And therefore can still cover a whole range of flexibility.
And Rachel, I want to ask the question that I get asked a lot and see what you have to say about this. You talk about specifying a library, a rich library, but also with lots of different algorithms in it, and that there's some constraints about computer time and memory. So can you just talk a little bit about when you did this, you used 20-fold cross-validation. How long did it take? How many algorithms did you have? How'd you decide to have 3 versus 20 versus 10? Can you talk about that a little?
Yeah. I'll actually go to the R code. So I included, I don't know exactly how many, but this many. And I tried to include those that were representative of what we had in the table. It took 30 minutes to run this superlearner, and I have this 20-fold cross-validation, but then also within each of those folds, another 20 folds to fit the superlearners. So that seemed pretty quick to me, considering the number of learners that I had. But I'm generally a bit more patient with the time it takes to fit, because I know that I do try to pre-specify it all, and you just run it once, so it's not that bad.
Thanks. It was good to get an assessment of that. So now we have another question in the Q&A from Ed Bain. Can you speak to how to compute standard errors for causal estimators when superlearner is used? For instance, since superlearner uses random splits in k-fold cross-validation, the actual splits used are based on the random seed used, and using different random seeds might lead to somewhat different results. Further, with discrete superlearner, the single algorithm chosen might differ from sample to sample selected from a common population. Similar issues arise with using ensemble SL. Other than using the bootstrap, the whole TMLE with SL procedure to compute SEs, are there any shortcuts?
Okay, so there's the one question about the standard errors, but then there's also the question about the single algorithm chosen by the discrete superlearner, or the weighted combination might differ from sample to sample selected from a common population. I don't really think there are shortcuts, but it's not that time consuming in general. And when we use more folds, I think that we tend to have more less variation, I guess, across differences that are induced by the k-fold cross-validation. Also, using the bootstrap would be more time consuming to compute standard errors. And what do you think, Susan or Mark?
Oh, I can. I mean, I think one point I think raised by this question is that there is a variability due to maybe the random seed, right? How precisely the samples are split, and yeah, that is one thing. If that variability is serious, which often it's not, but if it is, that means we need to do another layer of 20-fold. So we have to do like 2 times 20-fold and do 40 splits in the data. And in fact, I think that's a project Susan has worked on and a function for, which is some kind of stability of stabilizing the superlearner for that type of additional variability, which can occur in certain situations. And certainly, when the sample size is not that big and that kind of thing. On the other hand, increasing V usually gets you there. Also, yeah, regarding getting standard errors. Yeah, in first order, right, the asymptotics of TMLE tells us that we don't need to worry about a little difference in the superlearner. It's all going to be if the superlearner is doing a good job and achieves the n to the minus 1/4 rate of convergence to the true function, then the estimator minus truth will behave like the sample mean of the so-called efficient Immel's curve. And therefore, apparently all that choice of which particular superlearner you chose and what algorithms and what's sample splitting, they all have a second order effect, not a first order. Now, and also that establishes that the better job you do on the superlearner, the less important it's going to be, these extra little variability factors. And so it only means invest more into a great algorithm for the superlearner. And of course, nowadays we have the highly adaptive lasso, which really, is a real advance by having that guaranteed rate of convergence n to the minus 1/3. So these are the things which are going to add stability. So making the superlearner better will add that stability. Now, if you still say, yeah, but I still care about second order behavior because I want to pick up getting a better finite sample statistical inference procedure, yeah, then there are things you can do. You have to be a little careful because when you do the non-parametric bootstrap with things like superlearner, that's theoretically not completely valid, but there are ways to repair that by making sure that it doesn't do the cross-validation, like splitting a subject which is occurring twice in the bootstrap sample. You can't have that. So these are tricks which then make it, even the non-parametric bootstrap, reasonably robust. Again, with the highly adaptive lasso, you can do the bootstrap. And so that would, again, there's also paper on that, of how to use bootstrap-based inference for the TMLE when using highly adaptive lasso. So yeah, that's in general still interesting.
And then this is Susan. Rachel, did you want to say something?
I was just going to say, you were probably going to say it just about the stability with the discrete superlearner, that you found that it was always stable.
Oh, right. Just in my little experiments. Yeah. So I was going to actually talk about that a little bit. You can imagine if you choose n-fold cross-validation so that each observation is its own validation set, like leave one out cross-validation, then there's total stability. There's only, there's exactly one way to do leave one out cross-validation. And of course, if you have 1 million observations, then that's really overkill. Can't we do leave two out cross-validation? If we have 1 million observations, we certainly could, right? And as you start to realize that you get to choose V smaller than N. And so that's why, Rachel talked about that effective sample size. And again, it's a rule of thumb. The larger V you choose, the more protected you are about this instability problem, because there starts to be multiple ways to split the data, but they're inconsequential. So V equals 20, we sort of have informally set as the upper limit, because that's holding out 5% of the observations. And obviously you're going to end up evaluating your cross-validated risk on the whole entire data set. So each training set will be 95% of the observations. So you'll be training on quite similar training sets across the 20 folds, and you'll be evaluating on the entire distribution of the data when all is said and done and you've done the averaging. So V equals 20, we didn't see improvement beyond that even at small sample size. And at large sample size, it's really just overkill, as I was saying before. So you're right that with different random seeds, you get different splits. And so make V large will guard against that mattering. And as Mark said, it already didn't matter. Because if you're going to use this within TMLE, the targeting, you get asymptotic linearity and you're good to go. The other thing I wanted to say is that with discrete SL, the single algorithm chosen might in fact be different from sample to sample, but that doesn't mean it actually is a different model. Think about the fact there's some proof that SVMs with a linear basis function are equivalent to lasso. So you can imagine if those are the two things in your model, in your library, half the time it could choose lasso, half the time it could choose the SVM. But it's arbitrary at that point, because maybe they're the exact same model, and you don't know, so this or maybe the predictions from the model are so highly correlated, and I do see this a lot. If you have one candidate that's like XG boost with a maximum depth of 4 and XG boost with a maximum depth of 3, those two might end up giving predictions that are correlated like 0.999. It doesn't matter which one you choose. It looks like there's variation because the weights might be 0 and 1 in one run of superlearner, and that might be 0.5 and 0.5 in another. It looks like there's huge variations in the weights, but that doesn't matter because the convex combination, this is for ensemble superlearner, the convex combination is actually quite stable. And for discrete superlearner, it's 0 or 1, but the predictions themselves have hardly varied. So it gets, it's interesting. It's a great question, and it's interesting.
And yeah, this also what you're pointing out is also shows that if you're still seeing that by choosing a different specification of the superlearner, that the predictions are still really changing, that means your superlearner is not yet, rich and diverse enough. But once you have a real rich and diverse specification of the superlearner, then these predictions become in fact very, very stable, exactly like Susan said. And it doesn't even matter so much, how the weights are chosen exactly, or even which particular algorithm is chosen, because they all give overall the same predictions. But as long as there's variability, that just demonstrates we should, in a way, we haven't done a good enough job yet by really utilizing the superlearner.
Yeah, and as Mark pointed out in his response, when you're focusing on the standard errors for the causal effect estimator, if you don't do TMLE, then there's nothing to even say that those are asymptotically linear. So I'm not really sure how you do SEs for that. Whereas if you do TMLE and targeting takes us, a millisecond, nanosecond. What is doing superlearner is a time consuming part. But if you do the targeting and you manage to get asymptotic linearity, then suddenly everything is just easy and standard errors fall out naturally.
Yeah, that shows the power of the targeting, right? Because we are used to that if you just fit big models or even different models, then yeah, that all affects how the standard error is going to look like. And on top, there's no theory which really supports it. But once you do TMLE, that really creates suddenly approximately normal distribution and adds that stability. And in fact, show asymptotically in first order, it doesn't even matter anymore what your precise specification was of your superlearner, as long as they are going to the truth.
I don't see any more questions. So Rachel, do you have anything you want to add before we close?
No, I don't. Thanks for answering those questions really thoroughly, Mark and Susan.
Thank you very much for putting together this presentation and covering all the important points about what you have to think about when you use superlearning in practice. We really appreciate it. And thanks everybody for joining.